Okay, welcome to the second video. So this one is I can distinguish between static and current electricity and identify examples of each. So I'm just going to show you a few different examples of both. So this is also going to be an important concept. So the difference between conductors, insulators, and semiconductors. So insulators are materials that do not allow electric charges to move freely on or through them. Well, what I mean by that is, let's say that you've got power line, terrible power line, something like that. These are power line. An insulator is going to be something like what would I want if you wanted to survive and I had a long stick? What type of thing would you probably want to touch the power lines with? Would you want to touch it with a metal rod, or would you want to touch it with a long piece of rubber? You'd probably have a better chance of living if you touch this thing with a long piece of rubber, right? If I'm down here and I got a giant stick, that giant stick, if that's rubber, what's going to happen is that it's going to insulate me from those electrons. So the electrons you can think about are flowing through this power line, right? And if this rod is made of metal, then these electrons are going to take a turn and they're going to come down and zap me. If this rod is made of, oh, my head went away. If this rod is made of rubber, let's say, then these electrons don't flow nicely through this thing. So it's insulating me from these electrons that are going to kill me. So that gets the difference here. So insulators are materials that do not allow electric charges to move freely on or through them. That's about it. They just don't have extra electrons in them that can flow. And I'll show you what I mean in a minute. It'll kind of help to talk about semiconductors. So first off, insulators. I'll kind of talk. So if we had like a material, let's say, and this was an insulator, and you've got, you have a bunch of electrons in this thing, right? There's a bunch of electrons. There's a bunch of protons too. They're evenly spread out, right? If this thing is an insulator, then these electrons are stuck. They can't move. So they don't allow these, like if they can move, that's electricity, right? If the electrons are able to like move from here to there. But if they're stuck, then it doesn't conduct electricity. It's not allowing any of these electrons to move. So that's what a insulator would be. A semiconductor, all a semiconductor would be is that they can kind of move. They can move a little bit. So then they conduct a little bit of electricity, right? And that's like this situation. So we've got anything that's computerized or uses radio waves depends on semiconductors. That is kind of hard to explain why, but because these electrons don't move very well, we're able to use that property for computers and a bunch of other things. They're kind of strange elements that allow that. So a semiconductor would be something like carbon. You might have heard about silicon being part that makes up your computer, right? We make chips, computer chips out of silicon. We could also make them out of like these other, germanium is a common one that's in your computer. Yeah. And what it is, it's better if I go down a little bit. What happens if you think about, like, let's say silicon, Si, it has, remember we talked about in chemistry, like shells? In silicon's outside shell, it has 4 electrons. It's got 4 outside electrons. Remember that in order for something to be happy, it wants to have 8 in its outside shell. So what happens with silicon, though, is that silicon ends up being able to form these perfect lattice structure, where it's like these perfect squares or cubes if it was in 3D, where all of the electrons are being used. They're being used to attach to the other silicon. They're all being used there, and none of them are free. But every once in a while, one would be free. So you get this where sometimes they're able to move. Sometimes those electrons are able to leave. Sometimes they're not. But that's kind of it. It's that lattice structure that kind of usually makes something good at being a semiconductor. Yeah, okay. Moving on. All right, conductors. Conductors are probably the simplest to think about. If you've got like, metals, usually metals are good conductors. And if we've got like, let's say a piece of copper wire, and I was talking about, insulators, the electrons couldn't move. Well, in this case, the electrons are able to move. They can move quite easily through conductors. So the electrons are free to move through that thing. They don't really hold on to their protons very well, so they can just zip through there. All right, superconductors. Now this is the cool stuff. So superconductors, I was actually able to make a superconductor when I was in university. They're very strange. So they're a material that offer little, if any, resistance to the flow of electric charges. Like no resistance. That means that if you had like a power line that was made of superconductors, it could go all the way around the Earth and it would never lose any energy. It would be perfect energy. The energy that you gave it, like right when you put it in the power line, would be the exact same as when it came out the other side, which is bizarre because that just doesn't happen. You guys probably learned in grade 8 that there's in any kind of situation, any kind of transfer of energy, there's always energy loss due to heat, right? There's no loss due to heat with this thing. It's perfectly efficient. Like it's a perfect thing. So you might ask yourself, why don't we just use these things all the time? They sound like some kind of miracle material. Well, they would be, but they need to be cooled down to really, really cold temperatures, like minus 200 degrees Celsius for some materials. Some materials I think are like minus 100 or something like that, right? Like minus 120 maybe. I forget what they are now, but they need to be really, really cooled, and it takes a lot of energy to cool these things. So it's not really worth it in a lot of situations. But that being said, superconductors do have a lot of different. They do have a lot of different applications. So this one's not really a practical application, or like it is, but this is kind of a cool little lab that you can do. I did this one in university. We got to make our own superconductor, and if you put a superconductor, that's a superconductor, over top of just a magnet, what happens is it levitates. Which might not seem that cool because you know that magnets do that, but superconductors aren't magnetic. They just conduct electricity perfectly. And I don't want to get too much into like what's happening there. It's kind of I guess I will. What happens is that the magnetic field ends up going into the superconductor, right? So it's like you can think about like it being a magnet that it sends a current, like a magnetic field through it. Whenever you put a magnetic field through a conductor, it makes its own magnetic field. So when this thing happens, it goes through, and then this superconductor ends up making a new magnetic field. So they end up repelling each other because of that. It's just like it's kind of really cool. So it can levitate like that. So why that's kind of neat though is we can use that principle if you cool it down. You can see how cold this is, right? If you use that, we can use something like maglev trains, right? Where trains actually they hover on magnets. Well, right now we can do this with just magnets. They have to be like electromagnets to be strong enough, and that again takes a lot of electricity. But superconductors, if we could get these, like make some superconductor that worked at room temperature, then we could just have like mag trains that just floated without any extra energy. We wouldn't have to like make like we wouldn't have to make our own magnets or any of that kind of stuff that is a lot of energy. You could also have just like perfect hoverboards. That'd be cool, right? Yeah. So the other thing, so they use that for that, or they don't actually use it right now because you'd have to cool these tracks down so incredibly cold. MRI machines, in order to see inside like people, they need to make extremely strong magnetic fields inside there, so they need to use superconductors to do that. Okay, so almost finished here. So just want to quickly kind of go over again. So like the term neutralizing. So neutralizing unbalanced charges. We talked already about a like static electricity having a discharge is the movement of charges whenever an imbalance of charges occurs. Really lightning, right? That's kind of like a common example, but also like the power lines example that I was talking about, how if you've got a power line from there to there, there's an imbalance of charges in this thing because this thing has like really high electron. There's a lot of negative charge up here. The ground has, or you, because you're attached to the ground, has neutral, so positives and negatives are pretty much neutral. I'll draw negative symbols up here. Negative, 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 negative. So what happens, there's an imbalance there, and these things want to go to the ground if there's a path for them to go. So these electrons, if you stuck a metal rod up to that power line, they are going to neutralize, they're going to try their best to neutralize by sending these electrons down the metal rod into the ground. So that's neutralizing it. That would also be called a discharge of energy, or of electricity. So this would be, just so we got all our terms here, imbalance. There was an imbalance because you had more electrons up here than there was down here. Yeah, so it would create like a miniature lightning bolt. So same would be true with a cloud that had too many electrons up here. Remember, there's also protons and positive things up here too, but just more electrons. And again, if there gets enough, they're going to discharge. See if I can draw a lightning bolt. I am really bad at drawing. Okay. So they're going to discharge down to the ground, right? These are just electrons that are coming down. And yeah, that's kind of the concept. All right. Last thing, two methods for neutralizing an object. One is grounding. That's kind of what we've been talking about, right? So power line, metal rod. I've grounded this, right? What that means is that I've attached this thing to the ground. Like the ground is huge, so it's the entire Earth. So if I attach this like really negative thing, the electrons are going to want to go to the ground. They want to even out, so they're going to come down here. So that's what we call grounding. You can think about it as literally attaching it to the ground, so it can be absorbed into the whole sea of how neutral the Earth is, right? Now the other one, ionizing. So what ionizing is, let's say you've got, well actually a good example of this, I just kind of thought of this now. Clouds, let's say again, so we've got too many electrons, or a whole bunch more than protons. So if that's our cloud, have you guys ever heard of something called seeding, when they fly through with a plane and they seed the clouds? Well, what they're doing when they seed the clouds is they're going to fly through and they're going to spray a bunch more positive particles on this thing. And it's going to neutralize this because the electrons are going to want to go to those particles. They're going to move out of the cloud and go to those positive particles that we sprayed on it. Remember, it's the electrons that move. These are just like this spray of protons that they're shooting. That's actually like a mist, right? So they're still like in the liquid. The electrons are the ones that are going to move out of the cloud and attach themselves to these protons that we sprayed. So that's ionizing. Another just way of thinking about that, I guess, is if you had a balloon that was really negatively charged, that would just be spraying it with water, right? We kind of noticed in that lab that we did, if you sprayed it with water, then the water, so little droplets of water all over it, the electrons that were too many on the balloon all start moving on to those little droplets of water that you sprayed on. So droplet there, the electrons all move to the different droplets. So that's why you lose your charge when you spray it with water. Yeah. And that's about it. I'd like you guys to do page 271, questions 1 to 7 for me for homework. And I'll end the video there. So see you guys in class.